Today's notes are on evaluating and graphing polynomial functions. A polynomial function is a function in the form of ax to the power plus bx to 1 less power plus cx to 2 less powers, so it's in descending order by degree with a constant at the end. A, b, and c are going to be real numbers and the exponents will all be positive. Standard form is the form of a polynomial function when the terms are written in descending order from exponents from left to right. Direct substitution is what you're used to seeing when you plug in a number for the variable and simplify. For example, when I want to know what this polynomial is equal to when x equals 3, I plug in 3 anywhere I saw an x, and then we go through and simplify. Another way to evaluate a function is using synthetic substitution. For synthetic substitution, we have our polynomial. You're going to take the coefficients for each of the terms, making sure that you're including 0 for any of the missing terms. So that's step 1. Put problems in standard form, insert 0 for missing terms. Then you're going to set up your function, so you have the bar here. You're going to have your coefficients in the top of that space, like you see above, and your x value out on the side. You're then going to bring down the first number below the bar and multiply that number by the number on the outside and put it back inside in the next column. Then you're going to add those values together. So 0 plus 6 gives me 6. And you're going to repeat that again. 6 times the outside number, 3, gives me 18. I put it in the next column. I add those together. Then I do 10 times 3. Put it in the next column. Add them together. 3 times 35. Put it in the next column. Add them together. So the value of f of 3 is going to be the last number that you write in the corner in the bottom right hand corner. Let's look at an example that we can do together. So example 1. I'm going to start by setting up my problem. It is already in standard form. But when I set it up here, I want to make sure that I'm including 0 for any missing terms. So for example, I'm missing an x, so I'm going to replace it with a 0 as a placeholder. You're only using the coefficients, you are not writing down the variables. And I'm going to put my x value, which is my -3, out front. You're going to bring down the first term and multiply it by the number out front, so I get -12. I'm going to put that in the next column and add these numbers together to get -10. -3 times -10 gives me a positive 30. I'm going to add the numbers in that column together to get 30. 30 times -3 gives me -90, which I'm going to add to the -10 to get -100. The last number that you write is what f of -3 is going to equal. So f of -3 equals -100. Please try and do example 2 on your own. We're going to look at graphing a polynomial with a third degree or higher in class, so skip down to the part about end behavior. End behavior means what the graph of a function is doing when x, your domain, approaches positive infinity or negative infinity. The expression x, as it approaches positive infinity, this is how it's written, this is how it's read. X approaches positive infinity. End behavior refers to what is happening at the ends of the graph. To decide this, you're going to look at the first term that has the highest degree. If the term with the highest degree has a positive coefficient and an even degree, as x gets smaller, the y values increase, and as x gets larger, the y value increases. So both ends are going up. So the basic idea here would be the left side rises and the right side rises. In symbolic notation, you're going to have as x approaches negative infinity, then y approaches positive infinity, and as x approaches positive infinity, y approaches positive infinity. The x portion of this statement will always stay the same, only what I have boxed in red will change. So for the next one, if I have a negative coefficient but still an even degree, it says as x gets smaller, y decreases, and as x gets larger, y decreases. So as x approaches negative infinity, y approaches negative infinity. And as x approaches positive infinity, y approaches negative infinity. Again, the only part that's changing here is the part inside the y. Now it's going to look if you have an odd degree. If you have a positive coefficient but an odd degree, as x approaches negative infinity, y approaches negative infinity. And as x approaches positive infinity, y approaches positive infinity. The last one is when you have a negative coefficient and an odd degree. And the symbolic notation is as x approaches negative infinity, y approaches positive infinity. And as x approaches positive infinity, then y approaches negative infinity. So for example 4, it wants us to describe the end behavior of each function using symbolic notation. You were concerned about the term with the highest degree. So I'm only looking at negative 3x to the 6th power. The first thing that I'm going to look at here is that it is a negative coefficient and even degree. Because it's an even degree, I know that both ends of my graph are going to be facing down. Because it's an even degree, I know both ends of my graph are going to be facing the same direction. And because it's a negative coefficient, I know they're facing down. I also know that end behavior always starts with a statement as x approaches negative infinity, y is going to approach, and as x approaches positive infinity, y approaches. And I need to fill in the 2 blanks right here. So looking at my little sketch, as x approaches a negative infinity, so as it goes to the left, I can see that my y values are going down, which means that it approaches negative infinity. Then, as my x values are going to the right, I can see that my arrow here is still going down, which means again, y approaches negative infinity. We will talk more about end behavior tomorrow in class. Please try and do example B on your own.